Intro Algebra Lesson 2-1A. Alright, we're gonna start talking about numbers now, and in algebra we deal with quite a few different types of numbers. So our first little bit of info we'll go over to make sure we're understanding everything is real numbers. A real number, or sometimes known as a rational number, real or rational number, is any number that you would be able to put on a number line and it would have an exact location rather than an approximate location. I know that sometimes we take real numbers and we approximate where they go, but I'm talking about there's an actual spot for 2. There's an actual spot for 20. There's an actual spot for 1/2. There's an actual spot for the decimal 0.25. Now, a number that's not rational would be like pi. Pi continues on forever, has no ending. It doesn't even have a repeating decimal in it whatsoever. There is a number that repeats, but there's no pattern. They have actually found pi out to billions and billions and billions of numbers to the left of the decimal and never found a pattern that repeats or an ending. So it's irrational. We would not be able to find an exact location on a number line where it goes. We could only approximate it. Generally, we approximate pi to be 3.14. So on a number line, our negative numbers are always to the left. Our positive numbers are always to the right. Right in the middle is 0, which we could also refer to as the origin. Now I would be able to take this number line and go, here's 1, here's 2, here's 3, and on the other side, here's -1, here's -2, here's -3. And as you look at this, when you move to the left, it appears as if the numbers are getting bigger, when in fact they're actually getting smaller. The farther to the left we go, it gets smaller and smaller and smaller. The farther to the right, the bigger, the bigger, the bigger. We're pretty good with the right side. We're pretty good with the fact that numbers get bigger as they go to the right. But this is the one that always messes us up. Say we didn't have these numbers. Say we had -100. Many people think that -100 is bigger than -1. But it's not. -100 is much farther to the left. So in fact, it's much smaller in value than -1. The farther to the left you go, the smaller the value becomes. So just keep that in mind when you're looking at positive and negative numbers. Now 3.14 is pi. If right here is 4, 3.14 would be like right there somewhere. I don't know, I can't even get an exact spot for pi. I can only approximate pi's location. So that's why pi is not considered rational. So this box right here that I have, and I'll refer to it momentarily, this box represents all the rational numbers. If it's a rational number, if it's a number that you can put on a number line, then it's in this box. It's a special box. It contains all of them. So rational numbers, real numbers are in that box. From those rational numbers, we have a special club. It's like, here's a club full of all the numbers that can be put on a number line, but then inside that club is a special club known as integers. Integers can be positive, integers can be negative, they can even be 0. But they can't be decimals and they can't be fractions. So are integers considered to be real numbers? Yes. All of these numbers could be put on a number line and have an exact location. We don't have to approximate them. There are no decimals, however. So just because it's an integer is a rational number doesn't mean all rational numbers are integers, because any fraction, any decimal that's a real number is not an integer. So it's a special club. So within our rational numbers, which have all of them, is the special club. We have another group called integers. Integers fits inside. Every single integer is actually, all these integers are actually real numbers. So here's another club of integers. If it's a positive or negative number with no decimals or fractions and 0, it's part of the club integers. But inside integers is another club, more exclusive club, known as whole numbers. 0, 1, 2, 3, 4, 5, 6, and going on forever. ... means forever. Notice it does not let any of the negatives in its club. It lets 0 in, it lets 1, 2, 3, 4, 5, 6, no decimals, no fractions, just 0 and then all the positives. So inside integers, the club known as integers, is another special group that we just mentioned, known as whole numbers. Every single whole number that exists in the universe is an integer. All of these whole numbers are integers. And all these integers are real numbers, which means all whole numbers are integers. But not all real numbers are whole, not all integers are whole, only these numbers of the integers are whole. Okay, so this is a special club. But within the club of S, we have another special club known as natural numbers. And you'll notice the only number from the whole number clan that doesn't get into the group of natural numbers is the number 0. So inside this whole numbers group, we have one more special group known as natural numbers. Every single natural number is considered to be a whole number. Every single whole number is considered to be part of the integers. And every single integer is part of rational or real numbers. Alright, this is the whole group. So what is it if it doesn't fit in the group of rational numbers? Then it's referred to as an irrational number. Something like pi would go in here. A number that continues on forever with no decimal, repeating a pattern, or a termination of decimals. Now I just gave you a physical model of what's called a Venn diagram. Here's the exact same thing but on the smartboard. You'll notice that in here in the middle is the most exclusive club. The outside is the less exclusive club. Anything in the real numbers category can be fractions, decimals that terminate. Alright? These are all considered real numbers. But some of them are integers in here. These are all the positive and negative whole numbers. No decimals, no fractions can be inside this ring. Then a more exclusive club doesn't let any negatives in here. And a more exclusive club yet doesn't let 0. But all these numbers are real. All these numbers are real. All these numbers are real. So all the ones inside belong to the groups outside of them, but only some of the kinds can get inside the groups. Now, graphing means to put a number on its actual location on the number line. We also refer to this as plotting. So if you're being asked to plot a point or plot a number, you're being asked to put a dot on a number line where that number would go. So here's a number line, and I can label it anyway. If I was supposed to graph 7, say I had to graph 7 on a number line. Well, I would label the number line 0, 1, 2, 4, 6, 8, which means 7's right here. I would put a dot at the location where that number goes. That's been plotted. Alright? Maybe I have a different number. Maybe instead of 7, I want to graph -3. Okay, if I graph -3, maybe there's 0, there's 2, there's -2, there's -4. -3 is right in between -2 and -4. So that's the location for that value on the number line. That's what it means to graph. So I have graphed that number on a number line. You can graph more than one number. You could say graph 1. Okay, if I graph 1, that's right here. Maybe it says graph -1. If I graph -1, -1 is right here. So you can graph many numbers on a number line. Graph the numbers on a number line. Then when you're done, write 2 inequalities that compare. Remember, compare is what's the same, what's the difference of the two numbers. So we're going to write an inequality comparing the two numbers. So here are our two numbers, -4 and 5. It's going to be pretty easy to graph that. I'm going to start off by labeling my number line. I'm going to put 0 right here, which means this is 1, 2, 3, 4, 5, 6, 7. And over here is -1, -2, -3, -4, -5. And I'm going to graph those numbers. So -4 is right here on the number line. It's pretty easy. And +5 is right here on the number line. So I have now put their locations on the number line, and I need to write 2 inequalities that compare them. So here's how you do that. Is one of these numbers bigger than the other? The answer is yes. The number that's farther to the right is bigger than the number that's farther to the left. Always. Alright? So whatever number's to the right is bigger. One way we could write an inequality to describe this is we could say 5 is greater than -4. So that is one inequality that compares the two numbers. Now, is one of these numbers less than the other? The answer to that, yes. The number that is farther to the left is less than the number on the right. So the other way we could compare this is we could flip it around and say -4 is less than 5. There I have it. I have two inequalities comparing the two numbers. Now you'll notice all I did is swap the 5 and the -4. But when I flipped it around, the inequality sign also flipped around. Be cautious of that. Last bit of info here. Example number 2. Order the numbers in increasing number. Increasing means small to big. That's what it means for increasing. Start with the absolute smallest number you have and then figure out what's bigger. Now, here are the numbers. -1.5, the fraction 1/3. -3 is an integer. 2.5, 0, and -1. You've got a mixture of decimals, fractions, integers, natural and whole numbers. You've got everything you need here. There's a whole bunch. This isn't always easy, and I find that people make a lot of mistakes, especially when there's a mixture of different types of numbers. My suggestion for you, get everything onto an even playing field. Don't try to deal with them all together like this. Either decide to make them all fractions or decide to make them all decimals. But do something to get them all on an even playing field so it's easy to compare. In this case, since there's only one fraction, I would probably try to make this one equal to a decimal. If you take 1 and you divide it, because that's what this line means right here, division. If you take 1 and divide it by 3, you'll get the decimal 0.3333333 forever. So this is 0.3 repeating on forever. Now I have the approximate value of that fraction. I have this decimal, that one, here, here, here. I'm pretty good. I can now do the comparison. One little hint I can use, something else you might think about, you're comparing these numbers now, is you can use a number line if you're having a hard time seeing which numbers are smaller or bigger. The way you do that is you put dots for each one of these on a number line. And then you can tell which one's the smallest because whatever's farthest to the left is the smallest and whatever's farthest to the right is the biggest. So comparing numbers on a number line can be a pretty savvy way of doing this. I do have some negatives, I do have some positives, so I'm going to go ahead and put 0 in the middle. That would make this -1, -2, I'm sorry, those aren't negatives, positives. 1, 2, 3, 4, 5, 6, 7. And then I have -1, -2, -3, -4, and -5. I actually have plenty of room now, don't I? Plenty of space for my graph. Now, as far as graphing them are concerned, -1.5 is going to be halfway between -1 and -2. If this is -1, -1.5 isn't going to be here. It's not between 0 and -1. It's going to be right here, between -1 and -2. So here's my spot, -1.5. Then I've got 1/3. 1/3 is not 0. It's bigger than 0, but it's not a whole 1. 1/3 is somewhere in here. So I have 1/3. I've got -3. That's pretty easy to graph. -3 is right there. So I've already labeled that, -3. I've got 2.5. 2.5 is halfway between 2 and 3. So it's right there. 2.5. And I've got a 0. 0 is pretty easy to graph because I've got a spot for it. And I have -1, which is right here. Now, I can see all the dots, and I can determine their order very easily now. I have the smallest value is -3. The next smallest value is -1.5. I'm sorry, the next biggest. The next biggest number is -1, followed by 0, then 1/3, and then 2.5. And the only way I can figure that out is if I put them on the number line and see how they relate to each other. Remember, the number that's farthest to the left is the smallest, the number that's farthest to the right is the biggest. So I have now completed the order from smallest to biggest, increasing order, getting bigger. All right? The number line can be very helpful, especially if you're still kind of developing your skills with positive and negative numbers as well as fractions and decimals.